Welcome to the course in Advanced Quantum Mechanics. Maybe we should close the door just for quiet. Okay, so maybe we should start with a quick introduction. You are, I think, a small enough audience that I may at least try to remember your names. So let's just go. I'm Efrat.
Daniel Meisel.
Okay.
Always look here.
Okay. No?
I'm Samata, and I'm sorry I don't understand you.
No, you don't need to. Don't be sorry. Okay.
יוסי סלם. יונתן.
Okay. Okay.
רבי אפרת.
עקיבא גולדברג.
Zichen from China.
Okay.
אופק טבת. עידן אנש. דורון.
Okay, nice to meet you all. I'll try to remember the names. Let's start from the beginning. Sorry, I have time to erase this. What is this course all about? First of all, you all learned the quantum mechanics in your undergraduate studies, and the question is what is still left for us behind, that we need an advanced course first. So let me remind you what was the essence of what you studied in the undergraduate quantum mechanics. Mostly you talked about a single particle, right? You had so you learned all about the concept of a wave function that describes the quantum state of a particle, and then you learned how to solve the Schrödinger equation in various cases for various potentials and so on. You also discussed degrees of freedom such as the spin, right? So these are all familiar, but there were two things that made things relatively simple. First of all, the number of particles. Usually you talked about a single particle. That's one thing. And the second is that this particle always exists. Okay, so its wave function was normalized such that the probability to find the particle anywhere in space, for example, was 1, right? So you didn't consider the situation that the particle might disappear and turn into something else. But we know that this is possible. We know that the world is made of many particles, first of all, and we know that these particles can interact with each other. Okay, so there are forces in between them. They are not behaving usually as a free gas, but even if they don't interact, they just exist, but there are many of them. I believe you already mentioned the concept of fermions and bosons. Did you see that in your undergraduate studies? So for example, you know that solving the helium atom, which has 2 electrons, is more complicated than solving the hydrogen atom. Why? Because it's not only that you have some energy level and you can put one electron here, another here, and doesn't matter, there's no correlation between them. That's actually not true, because the electrons are fermions and they have to satisfy the Pauli exclusion principle, right? So in terms of the wave function of the two particles, it has to be anti-symmetrized. right? This is something I hope you've seen. Okay, if you didn't, never mind. But we'll talk about it a lot. And this is, so just going to 2 particles is complicated. And if you go to 3, 4, 17 particles, all identical, or macroscopic number, which is often what we're interested in if we want to describe electrons in a metal, for example, or something in the macroscopic world, you can have many, many, many quantum particles. And then the description from, just writing a Schrödinger equation for many particles is not trivial. Going from one particle to many is not trivial, even if they are non-interacting. Okay, so we would like to be able to describe large number of particles. Moreover, we want to be able to describe situations where particle number is not concerned because they can be destroyed or be created from the vacuum. Okay, so you probably heard at least a little bit about it qualitatively, that for example, in a photoelectric effect or things like that, when you have interaction between matter and light, photons can be absorbed and emitted, right? So they can be created and annihilated. The number of photons, it doesn't make sense really in reality to talk about a fixed number of particles, even if you talk about matter particles, not forgetting about high energy processes. If they are in an open system, particles can come in and go out. So the number of particles is not necessarily fixed, and moreover, it may not even be a quantity that has a well-defined value. You already know from the undergraduate quantum mechanics that physical quantities obey some uncertainty principle, right? So, for example, momentum and position, they obey a mutual uncertainty. And it turns out that particle number is also such a thing. So you can definitely have a quantum state that doesn't even have a well-defined number of particles. Okay? So all of this needs new tools. And the tools that you learned in the undergraduate, like the linear algebra of solving a Schrödinger equation, is and finding wave function and spectrum, is not useful. Of course, it's correct, but it's not useful. And we need to develop a new language, a new approach, and that's quantum field theory. It's an approach which is designed to describe exactly the type of situations I mentioned, that there are particles that can be created and annihilated, that they are identical particles that obey a non-trivial statistics like fermions and bosons. And that's what we're going to do in the main part of this course. Okay, there are other things that are included in the syllabus, but probably this year, unfortunately, because we had to shorten the course, we'll not get to it, and that's the Dirac equation, which is dealing with the relativistic quantum mechanics. So maybe just for completeness, we'll publish some notes on that, but I don't think we'll be able to devote a whole lecture to it. Okay, so I have to apologize, but we only have 10 meetings. Okay, yes?
Wait, do you have lecture notes?
Yes?
Yes.
In the course of time, I will post lecture notes. And,
Okay.
by the way, just reminding that we are recorded on YouTube, and there are also lecture notes from previous years, and there's a lot of material, that,
Yes.
including things that we'll not be able to cover in these classes. But of course, anything that you need for the final exam is
Do
going
you
to
have
be
recommended
yeah.
book for this?
Recommended book. So large part of the course is based on. First of all, it's all in the syllabus.
Mm-hmm.
But the book that I'm following at least part of the time is the book of Altland and Simons.
Can
Okay.
you write on the board?
Wait, sorry.
Inatus.
Okay. I'll use this. So wait, let me just see. You can see the whole board. But I'm not sure I remember its name. Okay, let me just I'll write it. I'll announce it on the model, but I think it's called condensed metal field theory. But
Yes.
I'm not sure. Yes. Anybody has? Okay, but there are many books, and you're welcome to look at them. And but I don't really think you need. It's not necessary to follow a book, because I'm not really following a book. I'm taking a little bit from here and there, but I like the general approach of Altland and Simons. So although this book is very much oriented to people who are interested in condensed matter physics, but the tools, the way they present the tools, is very useful for the majority of, what most of you read, or all of you, in fact. So, a lot of students here do their research also on condensed matter or optics, and both fields are very, very much suitable for this, the jargon that they use. Yes?
Where we can find the syllabus?
It appears in the, I don't know, in bar, in the model. Does it?
Sure.
I don't know. I mean, I see it in the system when I enter the. If you are registered, if you are officially signed. Yeah, every course has to have, and my syllabus is definitely updated, and it appears there, and I'm happy to post a copy also on the model.
It's very, very good.
Okay, and it will include also a list of references to books. Yes?
And you said before that we have an uncertainty in the number of particles, but the uncertainty that we know it comes with a dual.
You are asking a question about lecture number 7. I mean, we mentioned an example where this is an issue, but at the moment it is just a teaser. Okay. Yeah.
Okay, you said something about direct theory that you won't be able to cover it in the current course, but we will be testing on it, or?
No, of course not.
Okay.
You're not going to be tested on anything that you
okay.
didn't learn in the class. I thought this is.
There are some courses which do.
This should be clear, okay? Of course, you are going to do homework and to do the test only on some anything that I cover in the classes. And when I say classes, this includes the tutoring. So every 2 weeks, the second half of the lecture will be given by Sar Levin, who's the tutor. Okay, and what he's teaching or what he's showing in the classes is also important. Okay, so yeah.
How the grade is?
Look, this is, first of all, it's all in the model. Okay, the short answer is I think 20% is the homework, and it's compulsory. Okay, and the grade is only for submitting, not for. No, you are welcome to make mistakes in the homework and not in the exam. Okay, just do the effort, submit in time. Okay, Sar is going to maybe talk to you a little bit more about that, but it's 20%, so it's not negligence. Okay? And let me know also, let us know if you have troubles submitting in time for a good reason. Don't hesitate to tell in advance, please. Okay? So that's it for the formal things. Now let's do physics. Okay, so I want to bring you into the subject of quantum field theory starting from a starting point that is, I think, familiar to you because you all took wave theory in your undergraduate, and it starts from something, from a problem that you are basically familiar with, and I'm now going to review it, but formulate it in a way that will turn useful for us for the next more abstract stages. So, what is the problem that I'm starting with? These are phonons in, oh, actually, let me not call it phonons. Vibrations in 1D medium. Okay? So the problem is the following. We have a very long chain of masses. They are all identical. So let me draw them. Okay, and this goes a long way to both sides. In principle, the chain can have a finite length, but eventually we want to discuss it in the limit that this length can go to infinity, and in any case, we are going to be interested in the case where the length of the chain, the total length, let me call it L, length of chain, is much larger than the spacing between two masses. And all the masses have an identical mass that I'm going to denote by M, and they are connected by springs. Okay, so, and the springs they're all identical, and they have a spring constant K, and A is like this. The distance between two adjacent masses is denoted by A, and basically this is a lattice spacing. This is a one-dimensional, the simplest possible one-dimensional lattice. So this is the problem that I believe you have seen in solid state physics and in wave theory, right?
When you
Yep.
say A, you mean the
The equilibrium, yeah.
That's another קובץ.
Exactly. So A, let me write it down here. So M is mass of particle. K is spring constant. And A is equilibrium position, or equilibrium position. Okay? Okay? Okay. So, what is the dynamics of, so first of all, I want to write a Hamiltonian for this system. This is a very simple example for a system where there is a large number of particles, right? And they're all identical, and in this sense, it's a simple problem. But there is one thing that makes the problem not so simple, and that is the fact that the particles here are interacting. So if I try to move one particle, it pushes the springs and it applies a force on the neighbor. So there is an interaction between the particles, right? They are not decoupled. I cannot write the Hamiltonian as a sum over independent contributions like in an ideal gas. So this already tells us that although the problem is simple, the particles that I define here, which have a mass and so on, they are not good degrees of freedom in which to describe the system. There must be some simpler description, and we'll get to this description, okay? So let's write first a Hamiltonian describing the system, and when I say Hamiltonian, I want first to define momentum. Let me call it Pn is a momentum of mass n. Okay, so I have here, so in my chain, let me plot a few more. So I have n plus 1, n minus 1, right? So the index n is going to be counting. It goes from 1 to capital N, where capital N is the total number of atoms in the chain, or of masses in the chain, and N is the index of a mass that is positioned at some place, and P is the momentum, and I'm going to define Rn to be the position of the nth mass. Now, can you tell me what is Rn generally? So Rn is it's a one-dimensional problem, okay? There's only one axis. Let us assume that they cannot vibrate in the transverse direction, only in this direction. And quite generally, if I freeze the system at some time, what will be the position of the...
Maybe
yeah?
n כפול a plus some kind of a perturbation of, like
Okay, that's right. So generally, I'd like to say that at equilibrium, if I could put them all at the exact equilibrium position, all the masses will be, or the mass n would be located at n times a, right? But generally, that's not true because they have freedom to oscillate around the equilibrium point. So so there are going to be some deviations. So for example, this mass n can deviate. I hope this can be seen. Use a better. Okay, let me denote by phi n the deviation from the equilibrium position, and this, so the mass, if it deviates from its equilibrium, it's going to be located at the position that I denote by Rn, and this Rn is not equal to n times a, but it's n times a plus phi n. Okay, so let me write it explicitly. It's n times a plus phi. Okay, and phi, the way I plotted it, it happens to be positive, but of course it can be positive or negative. Okay, and this this phi is generally, if I'm thinking of classical mechanics of this chain, generally it's going to be time dependent, okay? And because I have some oscillation, and it's a dynamical variable, and if I want to study it classically, I need the equations of motions, and they're given they're derived from a Hamiltonian. So the Hamiltonian can be expressed in terms of momentum and coordinate. Okay, so let's write the Hamiltonian. So if I look at it as a classical variable, it's of course time dependent, right? And its equation of motion is determined by the derivative of h with respect to p and so on. I'm not going to write it because we are not doing now classical mechanics, but I know that all the information about this is included in a Hamiltonian, right? And once I have a Hamiltonian, I can also quantize it if I want. But let me start from this, okay? Right. So at the moment, actually, we are not going to do the quantization. We're going to formulate first the field theory, the way what kind of objects we have in the field theory, and then we'll use it to do the quantization. Okay? Yes.
Can you explain again what is it? Phi n?
So phi n is just the definition of the deviation from equilibrium, or it is, if you like, it is often we write it here. Phi n is actually Rn minus the equilibrium position, which is just a fixed value, okay? And it is also called displacement field in general, okay? And this is the interesting one. This is the deviation, and we are going to eventually work in the limit that it's small in some sense, but before I get to it, let me first write the most general expression, which is the Hamiltonian of the system is going to be is going to have two terms, kinetic energy plus potential energy. The kinetic energy is a sum over n of Pn square over 2m, right? So this is simple, it's just the sum of kinetic energy of the particles. But the potential energy includes interaction, because the potential energy is quadratic in the squeezing or dilation of the springs, and that depends not only on the deviation, on the displacement of one atom, but on the two neighbors, right? So to be more specific, we can write it like this. It's a sum over n. Of course, 1/2 k comes in front, it's all identical. And here we have Rn plus 1 minus Rn minus all that squared. Right? Exactly. So this difference, okay, so if we are at equilibrium, the difference between these two will be exactly A, and it will be vanishing. But if phi n plus 1 is different from phi n, I'm going to get something. And that's the elastic energy. Okay, and we see that the Hamiltonian is quadratic in this, yes? Because the elastic energy is determined by how much the spring is extended, okay? A is the equilibrium length of the, okay?
The delta.
It's the delta, exactly. In fact, if I'm using this notation for R, relating R to phi, I can simply replace this part. I can simply replace it by phi n plus 1 minus phi n squared, okay? And then the A completely disappears, okay? Because, as I said, again, Rn is Na plus phi n. Rn plus 1 is n times A plus 1, okay? But then I have the minus A. So the Na plus 1, okay? N plus 1 times A, sorry. Minus Na minus A is 0. Okay, so actually this depends only on the deviations. Okay? So I can actually forget about R, okay? Because and just work with the phi, because the constant here is just a constant, okay? Yeah. No, not here, okay? Just do it, okay? So just plug in this definition and you see that the A cancels.
It's plus 1.
Exactly, because it's plus 1. That's exactly the right, okay? Okay, good. Very good, so this is the Hamiltonian. The Hamiltonian is expressed in terms of momentum and coordinate. And I want now to switch from a Hamiltonian description to a Lagrangian. Have you seen it? So you all remember a little bit of analytical mechanics?
It is equal Lagrangian, so you want to just take T, the energy, and see this mention.
Right, okay, so I'm reminding you that Lagrangian is it's another way to formulate a dynamical system where we actually we do a Legendre transform, and we replace the momenta by velocities, which are time derivatives of the coordinates. And yeah, question? And the Lagrangian can be written as kinetic energy minus potential energy. Okay? And to be specific in our case, it's going to be, just erase this and rewrite it. So this is square of the deviation. So let me write it for our case. The Lagrangian description of this system is going to be a kinetic energy, which is a sum over n of 1/2 m phi n dot square, right? This is just kinetic energy in the language of velocity rather than momentum, minus the potential energy. And the potential energy is in fact exactly what I have here in the second term, which is the 1/2 k sum over n phi n plus 1 minus phi n square. Okay? Now, why am I going to Lagrangian? Because it turns out that a lot of the basic things of quantum field theory, when we don't know that much about the problem, this is not the case here. I'm starting from something we already know how to solve, right? You've seen it before, but the Lagrangian is the more useful thing, starting point when we don't know much about the problem, okay? And we just know that it has some coordinates and some velocities, some time derivative, and perhaps space derivatives. Okay, so that's the Lagrangian. Let me put it in a box. And if we have a Lagrangian, we can also define an action. Did you?
You integrate the L over time.
Over time, exactly. So that's right. So where should I put it? I think I can already. Erase this thing. Okay, so this is a Lagrangian, and the action is going to be just the time integral of L, and the time is from some let's say t equals 0 to some final time. It doesn't matter, it can be infinity, it depends on the problem you want to solve, but one can define an action as just a time integral of the Lagrangian. Okay? Okay, so that's just an expression, and the next step I want to take is to say, okay, so this problem is relatively simple, but there is one thing that I want to sort of generalize, and that's the fact that, you see, if I'm looking at the time dependence, the time is a continuous variable, but the space, which in our case is just along one line, along the x-axis, is discrete. I have a discrete number of particles, and I'm defining my Lagrangian in terms of the index of a particle. Okay? However, I'm interested in a very, very long chain, in the limit that the length, even if it's finite, is much larger than the spacing between adjacent particles. And we want to think of the limit where I have some macroscopic material, let's say a macroscopic string, okay, which in the macroscopic world it looks continuous. It looks like I have a continuous matter. Only if I go to the atomic limit, to angstrom distances, I see that it's actually made of particles, and the particles have interactions between them. So I want to go to the limit that we call a continuum limit, where if I have a large enough number of degrees of freedom, where the distances between them are very small, and I'm interested in length scales that are much larger than this microscopic scale. I want to replace the index n by a continuous variable, okay? And additionally, I'm making here an approximation. The approximation is that all the phi's, phi n, is much smaller than A. Okay, these are small vibrations. So if the vibrations are very small, also phi n plus 1 minus phi n, the differences between them are, let me put it in absolute value, these are also small. And if I want to look at the differences in this limit, you see quite immediately that to some good approximation, I can replace it by a derivative, right? A continuous derivative in the x direction. So that's the thing that I want to do next. So I'm now going to go. Yeah, sorry. You don't really need to do it because you can always look at the recordings later. Okay. So we're going to go to the continuum limit. Is it okay to erase the picture? Okay. So what am I doing here? I'm replacing. Let me define a coordinate x. So instead of having a chain with an index n that counts how many lattice spacing I have, I'm replacing it by a continuous coordinate that is just n times a. Okay, so this is what I do. I have the x-axis is in fact made out of intervals, but I want to go to the limit that the interval is infinitesimal, okay, or that a goes to 0, in other words, little a, okay? So here I denoted the indices by n and n plus 1, n minus 1, and so on. And now each n is just counting n times little a, and on the continuous axis I just call it x. Okay? Not x, is a is in X is going to be like our dx, okay, the infinitesimal interval, and therefore what before I defined as phi n, phi n, I'm going to replace it by okay, and notice that when I do this transformation, I deliberately include here some power of A, and we will see soon why. Okay, if I want to do it carefully, I'm going from something that is discrete to something that will become a continuous function. So the continuous function doesn't have the same units. Okay. In other words, if I'm plotting here, let's plot here a histogram of my fields, what I called before phi n. Okay, so on the x-axis, I have here some intervals, and here I have n minus 1, n plus 1, n plus 2, so on and so forth. And for each of them, I have some, on this axis, I'm plotting the phi. Okay? So this is phi n minus 1. This is phi n, and this is phi n plus 1, and n plus 2, and so on. But the phi's are very close to each other because the change in x from n to n plus 1 is very small, it's infinitesimal. And what is the continuum limit? I want to replace this discrete histogram of values of phi for each discrete value. I want to replace it by a continuous function, and that function is what I call phi of x. Okay? But you see that because to get from here to the continuous function, I have to somehow rescale it so it may have different dimensions. Okay? And we'll see why. Eventually, what I want to do is to take this Lagrangian and rewrite it in terms of the continuous variable x. And I will need to rescale the fields. And there is some freedom how to do it. The way I'm doing it is going to be the most useful for us. Okay?
What is it? X? It's
so again,
position.
x is this, if you like, a definition. It's a position. It's not a dynamical variable. Okay? It's just a replacement of the index. Okay? This is very important. So x itself is fixed. Okay? It just counts the degrees of freedom like before, but only it allows to convert it to some continuous coordinate. Okay? Okay?
X זה קורדינט במקום במרחב הרציף שמקביל על
Exactly. It exactly parallels the index n. Okay? That's what it is. And okay, so now the phi n also depends on time, of course, and it has a time derivative which appears here. And this time dependence will also follow to phi of x, right? It's exactly the same time dependence. So the phi, the phi of x is also a phi of t, but I'm not writing it explicitly here. Okay? Actually, maybe I should do it. Maybe I should do it just to avoid the confusion. So phi n of t, okay, is where time was already a continuous variable, is converted now to phi of x and t, a function of two continuous variables. Okay? Yeah?
למה היינו צריכים להכפיל את זה ב-a בחזקת חצי בשביל?
You'll see why. Okay? In the final thing, I don't want the a to be to appear in except through some parameter. Okay? Yes?
הכפל הזה בשורש A זה פשוט כאילו החלפת קורדינטות, אני יכול לחשוב עליו?
Yeah, if you like it is kind of like what you do when you want to change, when you go from a discrete variable to a continuous, sometimes you need to multiply by an interval. Okay, now I choose to do it with a square root. You'll see why it's more convenient for our case. Okay, actually you can immediately see why, because okay, let me go on and you'll see why I choose it like this. But what I'm saying, when you go from a quantity to a density of that quantity, right? Like probability and probability density. So, or from charge to charge density. So you have to integrate over. There is a dimensional change, right? Okay. But of course, what I'm saying, phi n and phi x have different dimensions. Right? Okay. Okay. So this is one thing. And now, and of course, if I look at phi n dot, which is the time derivative. How does the rescaling look? It's actually trivial because it's the time derivative of the same thing. So once again, I have a factor of a to the half and a phi dot of x. Okay? So that's obvious, but there is another thing that I want to do in the continuum limit. When I look, so here if I look at the first term in the Lagrangian, I only have a local field phi n, and I'm going to replace it by a phi x dot. But in the second term, I have a difference. And it's a difference between two quantities that are very close to each other. So what do I want to do in the continuum limit? I want to replace the difference by a derivative, right? And what is a derivative? A derivative is the difference between two values divided by the distance between them. And the distance between them is just a. So if I want to convert n plus 1, phi n plus 1 minus phi n, this difference, I want to convert it to a continuous variable. What will I get? So first of all, for each of the phi's, I want to rescale by a to the half in order to go to phi x plus a and phi of x, right? But in addition, phi of x plus a minus phi of x, let me write it down here, phi of x plus a minus phi of x, when the difference is very small, in the limit that a is very small, it goes to a times the derivative of phi with respect to a, right? So altogether, the difference is replaced by a to the factor 3/2 times a derivative of phi with respect to x. Okay, and in this course we are going to use this notation for the derivative, for the partial derivative with respect to x. Okay, because it's a partial derivative. Okay, is that clear? Why is the a to the 3/2?
No.
Yeah. So once, let me do it a little more slowly. Okay. So first of all, I'm doing it here. So phi of n plus 1 minus phi n, I first copy from here, and I get a to the half times phi of n plus 1 is converting to phi of x plus a, right? Minus phi of x. But phi of x plus a minus phi of x is the derivative multiplied by another factor of a. Okay, so that's why altogether I have a to the 3/2. Okay, very good. Now there is another last step I need in this mapping to the continuum. What is the last thing? In this expression I have summation over n. I want to replace it by an integral, exactly, but the integral is dimension full, right? So I have to divide by some factor of a to get the sum. Let me write it down here. So the discrete sum over n, everywhere, both here and here, I'm going to replace it by 1 over a integral dx. Okay? And the limits of the integral, if the chain is finite, is going to be 0 and L, but it doesn't matter. Okay?
Why not 10? Why not from 0 to n?
Why not?
Because n is
No, n. So again, n. The length L. I'm going to write it here. L is just n times a, right? Capital A. It's the total number of points times the length. Okay? Yes.
What we actually did here is that we had a summation over n, and then we replaced it to a summation over x, but the summation over x is technically an integral.
Yeah.
So we can practically say it's an integral from 0 to L when we actually replaced all the...
Right, but the integral has dimensions. Okay, and so if I really want to replace it, I want to just plug in.
Yeah, but how do we have to multiply by 1 derived by a? I mean, when we just do הצבה, because in infinite algebra whatsoever, we do remember to put the 1 divided by a when we want to replace a variable or whatsoever.
Okay, so it's a very good, excellent question. Actually, you have a freedom here. Okay, there is a freedom to define your continuous variable in some way that, as long as everything is consistent, you have this freedom. I choose to define the replacement of the sum in a way that maintains the dimensions, and define the phi of x to take care of the dimension. So the relation between phi x and phi n is such that the dimensions of phi are up to a factor of length to the square root of length. It's a choice. It's a choice of convenience. Nothing will change if I choose a different scaling. Why do I choose the 1/2? For convenience. because then if I do this, the first term will have no factors of A.
Okay.
That's all. But I'm always allowed to rescale my fields, to redefine them any way I like. Okay? What will change? Nothing will change except definition of the parameters. Okay? So let's see how it goes.
So you just define the movement from phi n to phi xt and the movement from the summation over n to the integral.
That's
so
right.
there will be so there will be no units.
Exactly, exactly. At least you're right. But it's perfectly legitimate to choose a different formulation as long as once you define this, these guys follow, right? So you no longer have the freedom. Yes?
And if I understand correctly, we started by saying that A goal is very small,
Yes.
but it cannot be 0 because then
Yeah.
this,
You have to take the limit that goes to
limit
0.
no, but not
Right. That's right. Okay. That's right. Okay? Okay, shall I go on? So these are just definitions, and once I stick to them. Let's see if I have space. Yeah.
Before you raise the part in the most left area, I want to ask you about something. When we say that phi n must be much smaller than a and phi n plus 1 and all that, is it like did we write them so the highest one, the phi n is very smaller than a, is fit into the phi n replaced by by the power of half? זאת אומרת, מה שרציתי לשאול זה, כשאמרנו שפי n ממש קטן מ-a, זה מתאים לזה שפי nt הולך להפוך להיות a בחזקת חצי פי xt, או שהדבר השני מתאים לדבר השני של פי n דוט t.
I'm not sure I understood that. First of all, this is just an approximation that justifies, essentially what it justifies is this stage, that I go from a difference to derivative.
Yeah.
You know that actually this is, this is exact, right? This mapping is exact.
Yeah.
But going from here to here is an approximation, right? It's taking the limit that a goes to 0. Because this is the definition of a derivative. Let's write it here. This is actually true, right, for any continuous function. This difference divided by a is in fact the definition of the derivative only in the limit that a goes to 0. Okay, so this is actually where I made an approximation, the continuum approximation. Yeah?
Again, about the limit, can I explain?
I'm saying that this, what I wrote here is just the definition of a derivative.
Yes.
It's not, I have to take the limit that a goes to 0 to get the definition exact, right? What I do in the continuum limit is I don't keep writing a goes to 0, but this is what I have in mind, okay? And in fact, if I, if I allow my phi's to vibrate very strongly, then it is not correct. And then if I want to do some expansion in derivatives, I will have to include higher derivatives, and I get something very complicated. But I'm not interested in that. I'm actually interested, and that's very important to stress right now. What is field theory doing? We are always interested in the lowest energy sector, okay? Well, some approximations are good. Otherwise, the full microscopic description of a system of many degrees of freedom in general is very complicated. We can plug it into computer and we'll find corrections, okay? But we are always going to think about this limit, that vibrations are small, that energy is low, that things are smooth, okay? So the continuum limit, okay, I have here the word is a limit, okay? It's not an exact method, but it's a very well justified limit when we have 10 to the 23 particles in the chain, okay? And if we are interested in distances that are order of magnitude larger than the microscopic scale, okay? So let's write down the result. If I plug in these definitions, what I get is actually, let me, although it wastes a little time, I'm writing here on the side just okay, this is the discrete version, and I'm now plugging the continuum limit, and what I get is that L is, so in the first term, the 1 over A will exactly cancel A to the half square. So you see, that's why I chose this scaling, and I get an integral over dx. The first term will now give me just half m phi dot square, okay? Minus, now in the potential energy, I don't get rid of the A, okay? Why? Because here I have A to the 3 halves. So what I get is, in fact, something like this, which I will define in a minute. This is what I get, and you see that here I defined a new parameter, rho s is the same k we had before, times a squared. Okay?
What do you mean when you put with brackets? It's only brackets?
Ah, these are brackets, yeah.
Ah, it's only second.
No, yeah, no. Yeah, sorry.
Not
If you don't like them,
It's okay.
if you don't like
It's
them,
okay.
I'm happy to write it with. Yeah. Maybe actually, you have a point that maybe it's. I should be careful in this particular course and not use curly brackets too often just for brackets. It's just that I don't like double brackets, but that's an aesthetic thing. Okay. Okay. So this is just to say that everything here depends on x, and you integrate over x. Okay? Okay, now notice that I had to define a new parameter. And in this parameter, the A does appear, okay? But it just appears in a way that sets the units, okay? So for example, if K is a spring constant, then K times A squared is a force. Okay, it's like a tension force, if you like. Or, in fact, it has a name. Why I denote it by rho S. What is the S? It's called a stiffness. a stiffness. It describes how tight is the string. Okay, that's all. But it's just a parameter. Yeah.
Stiffness is all the rho s, or is it just?
Yeah, rho s.
Oh.
Yeah, it's the name of the physical quantity, what we call stiffness. And it's this is what we need when we talk about elasticity of a continuum medium. We don't talk about spring constants, right? We talk about tension force or something like that, and that's called stiffness, okay? So, but the fact that it's related to K and A, I don't care. I have in my theory, I have two parameters, okay? A mass and the stiffness. If I rescaled my fields differently, I would instead get something like a mass density and something else. But it doesn't matter, the theory would be the same. Actually, what most of the physics cares about for this particular simple problem is the ratio between them in some sense, right? So there are two competing terms and they are just parameters, okay? But why do I like this, this form better than the discrete? Because it has a nice symmetry in it. Here I have a the square of the time derivative, and here it's of the space derivative. Okay, actually, if I want to make it look more symmetric, so to speak, instead of writing phi dot, I could write time derivative of phi. Okay, so it's a function of two variables. This field, phi now becomes a field. It's something that has, it's a smooth function, or maybe not even smooth, but it takes a value at each x and each t. It's a function of two variables. Okay, and that's the continuum limit of the Lagrangian. And now the quantity that I have here in the brackets is something that after integration over x gives me a Lagrangian. So what would be the proper name for just the
Lagrangian density?
It's Lagrangian density, exactly. So let me give it a slightly different notation. This I can erase now. Don't need it anymore. So this expression inside the integral, I call it Lagrangian density, and it's denoted by a curly L, and it's a function of, let me write explicitly, it's a function of a field. It's actually not a function, it's a functional, because it's a function of something that is a field itself depending on variables x and t. And the most general Lagrangian density can depend on the field itself and on its space derivatives and on its time derivatives. Okay? In some theories, it can also depend on higher derivatives, but we'll usually be left with this. But it's only a function and its derivatives. Now, in this particular Lagrangian density, there's actually no dependence directly on phi, only on its derivatives, right? We have one term that it goes like the space derivative, and the time derivative. Okay? But there could be some other theories that has a term that goes like phi itself squared, a local term. Yeah?
This Lagrangian below, that is not equal to L, big L.
No, so this is curly L, okay, and the connection is that L is the integral of curly L, okay? Okay, and curly L depends on X through its variables, okay? Now, I can go one step ahead. So the Lagrangian is an integral of a Lagrangian density. And it's an integral only over space. If I also integrate over time, what do I get? The action, right? So, in fact, let me write down something even more general. Okay, so this is just the Lagrangian. The action, which is the integral over time of the Lagrangian, is integral over time, integral over space of a Lagrangian density. Okay? And what I wrote here is actually very general. It's not only for this problem, it's a generalized thing. So in principle, formally, I can think of x and t as two coordinates, okay? And if I have a higher dimensional problem, what will I get? Right, I can have higher dimensional fields. Where phi depends not only on the x-axis, but also on y and z. And then the space becomes r vector, and the integral over space will be over three-dimensional space, let's say. Okay, or even a higher dimensional if we think of more abstract theories. Okay. Okay, so. Last thing before we want to take a break. Up to now, I actually did classical mechanics because there's nothing quantum. I just formulated, I wrote Hamiltonian, and I converted it to Lagrangian. I went to the continuum limit. This you can do in classical mechanics. Eventually, I want to quantize it. And in order to quantize, it's here I actually know already from the beginning how to quantize because I started from coordinate and momenta, and I know how to work with them from my undergraduate quantum mechanics. But in many problems, it's not the case. And I want to be more systematic. I want to get to the quantization starting from a theory. And the next thing I want to do with this theory is derive equations of motion. From the equation of motion, I will get some insight on what are the canonical quantum variables or operators that I want to do when I do the quantization. Okay? So the next thing I want to do with this Lagrangian, or rather with the action. Okay, so let me now write the action. Explicitly for our problem, I have an integral over time integral over space of the Lagrangian density, which is just half m phi dot square minus half rho s okay, this is the action. And let's say that the space and time, they have some fixed limits, length and time. Okay, and now I want to derive some equation of motion that describe the dynamics of the system. How do I do it? Remember from analytical mechanics, what is the general principle that gives us for any physical system?
Minimal action principle.
Exactly. Okay, that's right. Exactly. So we know that.
Variety. We need to do Euler-Lagrange.
Okay. So we want to get. That's right. We want to get to Euler-Lagrange, but let's do it for this problem. What is the deep principle behind it? Is to look for a function phi of x and t that gives minimum to the action. Okay? And this is the variational principle. Later in the course, we actually will see some reasoning behind it that is actually rooted in quantum mechanics. Yes?
Where we can see here quantization?
No, here there's no quantization yet.
Okay.
Okay? But eventually this will be our goal. I want to, again, I'm starting from a problem that is simple, and I could do the quantization before we started. But I want to show you all the steps so that when you come to a new problem, you just follow the recipe and then you are on safe ground. Okay, that's the logic. Okay, so we have a Lagrangian, we have an action, and we want to ask what types of functions, what set of functions phi x and t will give minimum to the action. Okay, so in other words, we ask the following question. I want to look for a minimum condition so that if I look for an action which is a functional of phi plus some deformation. Okay, so suppose I found I take some field, and I add to it a deformation that itself is also a function of x and t. And this deformation describes some function, but I multiply it by a parameter epsilon. And epsilon is going to be small. This is something that I'll take to 0. And I now define a delta S to be, so we can erase this. I define delta S to be the difference of this minus the action of the original phi. And I want to look at it in the limit where epsilon goes to 0. And in this limit, I want delta S to go to 0. Okay? Let's do it quickly.
Maybe you can change it now.
Yeah, I think I need to change it already.
Make it small.
I think I have a better one. here. All right, so let's do it quickly. So what do I get? So if I'm taking the if I'm plugging here a leading order in epsilon, what I'm going to get is sorry, actually, let me be a little more. Let me be more careful. So I want to define delta S over epsilon, where let me call this delta S. And what I want to get is that delta S over epsilon in the limit that epsilon goes to 0, this will go to 0. Okay, so it's not that the difference will go to 0. I have to divide it by epsilon to get a derivative. Okay. Okay, so what does it give? So delta S over epsilon equals, let me first do the expansion, and I'll write the leading order. It's going to give me integral dt integral dx of minus rho s times dx phi dx eta. Okay? That's the result. How do I see it? So if you just plug in this expression phi plus epsilon times eta, you are going to get something that has only the phi in it, and this will cancel with the second term. And the leading correction will come from the linear order in epsilon times phi dot times eta dot, and the same for the second term. Okay? Do I need to show it?
Okay, yes.
So let me just do the first term and you see. So phi plus epsilon eta square is, sorry, this is the dot, okay? This is, I'm just looking at the first term, and I'm plugging it into here, okay? So this square is phi dot square plus 2 times epsilon phi dot eta dot plus epsilon square eta dot square, right? This is exact. But now, when I take the limit, so let me write it like this. When I take the limit that epsilon goes to 0, the second term will divide with the epsilon, and the second term, the last term, will just give me with epsilon. And then epsilon goes to 0, and I can throw it away. Okay? So if I just keep in the limit that epsilon goes to 0, I need to keep just the leading order. And that gives me a product of phi dot eta dot. Okay? And the factor of half is cancelled with the 2. Right?
Wait, but what happens to the 2 to the phi dot squared?
So that cancelled because it's delta S. Okay? So the 0 order cancels. Okay? Okay? I'm just Maybe you better do it for yourself, but that's basically it. The first order cancels, and the second order in epsilon is just going to 0. Okay? Okay, let me do one more step and we'll go to a break. Yeah?
We throw it away the epsilon squared mu dot squared because it's negligible, or because
we take the limit epsilon goes to 0.
So because it's negligible, not because it's exactly 0, but because it's negligible compared to the.
That's right.
Okay.
Okay, here I already take the limit.
Okay.
The right hand side is already after taking the limit at epsilon goes to 0.
Okay.
Okay. Okay. Just last step, and you will see that we get something that you recognize. So what we require that this will be 0 in order to get a minimum, right? This is the minimum condition, is that the derivative of the delta S goes to 0. Okay? Of course, we also have to prove that it's minimum and not maximum, but let's not do it explicitly. It will be. But here I just want to see how you get the condition for the minimum. Okay? So this is the condition, and it's not very convenient because here I have an expression that has derivatives of both phi and the eta, and the eta was some arbitrary deviation that I added. Okay? Now I want to do one mathematical step. When you have such a combination of a product of two derivatives, you can always do integration by parts, right? What happens when you do integration by parts? So basically, I want to put the derivatives of eta to turn it on the phi again and get a second derivative of phi. Exactly. So when I do integration by parts, I always get the first term is going to be a boundary term, right? Because it's the integral. You saw it many times. And then minus the stuff that puts the derivative on the other function. Okay? That's basically integration by parts. Now, why is the boundary term always 0?
שאנחנו מניחים, כשאנחנו עובדים קודד הזה של הפונקציונל והכל, אנחנו מניחים שמראש הניו הזה הוא צריך להיות 0 בדיוק בקצוות של התחום של איפה שאנחנו.
Okay, so let me translate to English and say it more precisely. So we are looking at a family of solutions that on the boundary, they satisfy some boundary conditions, okay? Boundary conditions are part of our problem. Now we are allowed to deform our field in some arbitrary way, but such that the boundary conditions will remain the same. So the boundary conditions on eta are that it must vanish on the boundary. Okay? So under this assumption, what we get is this is where I stop. So after integration by parts, what I get is that delta S over epsilon is going to be minus an integral over t and over x of what will remain here is m phi double dot minus rho s of second derivative of phi. All that is multiplied by eta, right? Because if I do integration by parts on the first term, and the time derivatives go to the phi, and I'm left with just eta. And here it's the same. So altogether, I get an integral of eta, okay, and it's this eta of x and t, multiplied by something in the round brackets, okay, and all of that has to be equal to 0. And again, this is true for the limit that epsilon goes to 0. Okay, so what I'm basically getting is the following conclusion. In order for minimizing the action, the condition is that if I take an arbitrary eta, any function, and I plug it into this expression and integrate over all x and all t in my boundaries, I will get 0. Okay, how can it happen? How can it vanish for any eta? Okay?
It's a maximum.
No, it's a much more basic. I have an integral that must vanish, although I'm allowed eta to be anything I want, except, of course, it doesn't have to be infinity. Exactly. So the only way this will vanish for any eta is if the expression here is 0. Okay? Is that clear? And what is this? I think it's something you have seen. This is specifically for our problem, which is a 1D elastic medium. It's the equation of motion that actually gives you the wave equation, right? This is a wave equation. If I change, I move this to the right-hand side, and I write also the time derivative as a partial derivative, I get something like m dt squared phi equals rho s. Okay? You're familiar with this? This is nothing but a wave equation, right? Which describes the simplest type of propagating wave you can have in a 1D medium, where what is rho s over m? What does it define? Remember this from wave theory? So just dimension, let me hint, dimensions, okay? Here I have space derivative, second derivative, and here I have time derivative. No, I'm asking a very simple question. Yes. Thanks. Right. I'm asking what is the ratio? Okay. So actually it's velocity square. So rho s over m must have dimensions of velocity square. And what is this velocity? It's the velocity of the propagating wave, right?
But where it's not a wave. It's not a wave, yes. It's
No, I'm
the
saying
same.
the solution, this is an equation of, this is a differential equation that has infinitely many solutions, but it's a wave equation. A wave equation in general is something that connects space and time derivatives in some way. And this particular one has infinitely many solutions that satisfy that any function that you can write as a function of x minus vt or x plus vt are solutions, right? So it describes the family of solutions is a family of functions that propagate, okay, here it's actually plus or minus, right? Because you can have a propagating, because it's a second derivative, you can have propagation to the right or to the left. And, okay, so I can have any function that is something that propagates to the right. I can write as a function of x minus vt, and if it propagates to the left, I can write it as phi of x plus vt. And phi can be actually any function, so that equation has very little information. That's all it says, that any disturbance I made in this medium will propagate with a constant velocity, and the velocity is determined by the ratio of these two parameters. Okay? And that's just the simplest way. This is what we were supposed to see in the first lecture on wave theory. Okay? So up till now, I presented a simple problem. Let me write again the Lagrangian density of the one-dimensional chain, which is okay, and
Today we will see the quantization? Today we will see the quantization?
not yet.
Not yet.
But I think next week you will. So this is a Lagrangian density of a particularly simple problem that started from mechanical vibrations in an elastic one-dimensional medium. And it's describing everything in terms of a field that is some general function of x and t. And let me just summarize briefly what we got in the first lecture today. First of all, we saw that we can write the action as an integral over x and t. Oh, this is also not. Oh, yeah. Running out faster than expected. So we have a Lagrangian density of phi dt and dx of phi. We know that the minimum action condition will give us equations of motion. This is something we know from analytical mechanics in general, for classical mechanics, but in the field description, all we did today is just to generalize it to a case where you don't have just one degree of freedom, one particle with some dynamics, time dependence, but rather we have infinitely many degrees of freedom that form a continuum which you can describe by a continuum coordinate x. And instead of just one coordinate that might have time derivative, time dependence, we have a field phi which also depends on the x direction. And this x direction is essentially counting degrees of freedom. Okay? But otherwise, everything we know from analytic mechanics, we can copy, and in particular, we know that the delta S, let me write it like this, delta S to delta phi equals 0 is a minimum action condition. If we plug it in by defining some deformation of phi and looking for a functional that minimizes, that gives 0 for any deformation of phi, I see that what I get is an equation of motion. And again, because the equation of motion is not just for a single particle, it doesn't only have time derivatives of some coordinate, it has both time derivative and space derivatives, okay? And this is general for the particular case where the Lagrangian is this simple elasticity theory. I get that the equation of motion is nothing but what we recognize as a wave equation. And this is an equation that describes a wave that propagates with a fixed velocity, and the parameters of the theory, rho s and m, are dictating the velocity, okay? And they give us all the information we can get from this theory. Now, the next general thing we want to do, which for this particular example is already kind of redundant, but for a general problem, we'd like to know how to do it. We want to go now back from a Lagrangian to Hamiltonian, okay? So, of course, here we started with a Hamiltonian, but in many other problems, and we'll see one already today, we don't start from Hamiltonian, we start from a Lagrangian. This is the more basic thing that we can formulate in field theory. And from the Lagrangian, we want to derive a Hamiltonian in a general way. Yeah, there was a question?
Just do Legendre transform.
Okay, so the first thing I want to do in order to define a Hamiltonian, what is the difference between Lagrangian and Hamiltonian? I want to replace the time derivative of phi by momentum, okay? It's a change of variables. Yes, and you're right, we have to do a Legendre transform, but before we do it, we have to define the momentum operator, okay? Okay, now, in this case, we more or less know what it is, but let's derive it systematically. So what is the definition of a momentum operator? If I have a Lagrangian with some explicit functional of phi dot and phi, and the derivatives of phi and so on, what is the momentum? How do I define momentum if I don't know anything about the problem? Remember how to do it? Almost, yeah. So that's, let me now write a definition of pi, and I'm calling it pi, not p, okay? Now pi is also a field, okay? It's a continuous field, it's a function of x, is actually defined as the derivative of the Lagrangian density with respect to phi dot. Okay? And if you like, this is actually a definition. Okay? Now let us see what it gives. And after I define a momentum, then I can do the Legendre transform and I get the Hamiltonian. Okay? So let's do it. And let's forget that we already know the result, but we start from this and we define the momentum. What do we get? We take the derivative of L with respect to phi dot. What is it?
Okay.
It's just m times phi dot, right? Okay, great. Or, in other words, and phi dot, which is also a function of x, I'm writing it explicitly. So I can also invert this relation and write phi dot as pi over m. Right? Okay, and now let's do a Legendre transform to get the Hamiltonian.
Shouldn't we also mention this is reliant on time too, the pi xt?
Both of them depend on also on time. Yeah, you're right. Yeah, but let me just not write the time explicitly, but we know that it's actually everything here. All the fields that I define are functions of x and t.
And
Okay.
pi?
The pi also. Yeah, yeah.
Also,
That's that's exactly what.
Okay.
Okay.
The
All right.
Lagrangian is also
No, the Lagrangian is a function. It's a functional, right?
Oh, yeah.
It's a functional. Okay, it's a functional is a function of functions. Okay.
Yeah. I'm not denying that, but it's still like reliant on space and time.
Yes, because, but it depends on space and time via the
Just like
field.
the fields.
So in fact, it is. So that's why I write it. What I mean by this notation is that it depends on various fields, which are basically a field and its derivatives. In general, by the way, this is a simplification. It can also depend on second derivative in time, and you know. Okay. In more complicated theories, there are infinite. It depends on infinite types of functions. But usually we don't want to keep all of them, right? Most of the theories that are useful for anything, or it's enough to go to the lowest derivative, because, and again, it's justified by the low energy, small deviations, etc. Okay? But the fields are functions of x and t. And that's why if you think of them as classical fields, you can get an explicit expression for the action by doing an integral. Okay? But in the integral, you have to you plug in a particular phi of x in this. Okay? All right. So the first step to go from a Lagrangian to a Hamiltonian is to define a momentum. The second step is, once we have the momentum, we can write the Hamiltonian. So first of all, let me, just like before, I define a Hamiltonian density. And the Hamiltonian density will be a functional of pi and of phi and of their derivatives. Okay, so it can have additional terms, but it doesn't have phi dot. Okay, it has phi and pi. And possibly derivatives. Okay?
And why doesn't it have a phi dot?
Because that's what the Legendre transform is replacing the phi dot dependence by a pi.
Ah, okay.
Okay?
Okay, so it has a derivative of the pi dot, right?
No, there's no pi dot. There's no time derivatives. Okay, the dynamics, so that's very important. They can be space derivatives. But the time derivative is replaced by the notion of momentum. Okay? And that's just like for the analytic mechanics of a single particle. Okay? So, okay. So, first of all, this Hamiltonian is integral of Hamiltonian density, and the Hamiltonian density is given by the Legendre transform, which is pi. And when I say pi, I don't know if I want to carry it all the time, but let's do it for now. Everything I write in is a local field of x and t minus the Lagrangian density. Okay, where the Lagrangian density is a functional of phi and phi dot and stuff. Okay? Okay, so these are the two steps. I give you a Lagrangian, no matter how I got it, but here I actually got it from some microscopic theory, but it's not always the case. I define a momentum, I have an Hamiltonian, and the result for the Hamiltonian should not have any phi dot in it, only pi. Okay, it's important. Remember it in the exam. You will lose points for it. Okay, let's see how it works for our example. Okay, so this we don't need anymore. Okay, so let's take this Lagrangian.
So the 3 points are the other derivative in a space, right?
Yes,
Okay.
yes. Right. So I'm getting, let's first find the momentum. The momentum field, okay? It's a momentum field. From the definition, I take the expression for L and take the derivative with respect to phi dot. What do I get? We already did it. So actually, you know what? Let's, okay, this we already did. Okay, this is the general expression. And what I did here is already an example. Okay, so in order not to confuse you, I'll write it. I just rewrite it here, and that's it, okay? So I get that phi is n times phi dot. And then I now plug it into the expression for the Hamiltonian density. So notice that here the first term is pi times phi dot. But what is phi dot? Phi dot is no longer allowed to appear explicitly, but this equation tells us that it's nothing but pi over m, right? So the first term becomes pi times pi over m, okay? Minus the Lagrangian density. Okay, now let's do it slowly. So the first term becomes just the square of pi divided by m minus the Lagrangian density, which has 1 over half m phi dot square. But what is phi dot square? I want to write it here explicitly. It's pi over m, right? So instead of the phi dot square here, I write pi square over m square, right? And then minus 1/2 of rho s grad x, so it becomes a plus 1/2 rho s grad phi square. Okay? And if we combine these two terms, we see that they're actually pi square over m minus 1/2 of pi square over m, right? Which is plus 1/2 pi square over m. And together with the potential energy, what we get from it is, can I erase this already?
Yes.
Let me just copy, I want to copy this here. Pi is d phi dot, and h is pi phi dot minus. Okay, these are general. Okay? So what we got for our example, we get that altogether the Hamiltonian, which is an integral over x of the Hamiltonian density, where the Hamiltonian density is pi square over 2m plus rho s grad x phi square over 2. And this is it. So it's integral over x pi little clearly h is integral over x of pi square over 2m plus rho s over 2 This is the Hamiltonian of the system. And at this point we are going to stop before continuing, but notice that this seems to be already a good starting point for doing quantization. Why? Because we know that the connection between phi and pi, both of them are fields now. They're not just one variable. They are fields that depend on space and time. But for each point in space and time, phi of x and t and pi of x and t are related by what kind of connections? They're like coordinate and momentum, right? And if they are coordinate and momentum, in quantum mechanics, we know that they satisfy some commutation relations that are canonical. Okay? So we are going to use it, but not today. What is the reason I don't want to do it today? Because in this form it's still not useful. We noticing that in the potential energy term is not dependent on phi itself. It depends on its derivative. And the derivative is not conveniently, so we have to work out a little bit how the commutation relations work, okay? It's a non-local thing, and in fact, you can probably guess what we're going to do in order to make it very good. Yes, exactly. Okay, so this will be the direction. But let's just stop here because I now want to go to the more general picture, and we'll get back to it next week. Okay, so I gave you some general prescription for how we deal with a field theory, which, if I want to summarize it in the most general terms, is first, find the Lagrangian. Okay? How you do it, it's your problem. As far as I'm concerned, guess it. Just guess it and see what you get from it. Okay? And I'll give you soon an example in which cases we can make a guess. Once I have a Lagrangian, there are several things I can do with it. First of all, I can look for a minimum action condition, and this will give me equation of motion. An equation of motion is already a partial differential equation that I can solve in some approximation or the other, or even exactly in some cases. Okay, that's one thing I can get. So it gives me information on the quantum, on the dynamics of the field, but that's classical. That's classical. The second thing I can do with it is go to Hamiltonian by using this prescription. Okay? And this prescription is always correct, no matter what is the physical meaning of phi. It can be some generalized field. Okay? I mean, it doesn't have to represent coordinate or space-like object. And after I got this, I have a Hamiltonian, and the Hamiltonian is expressed in terms of the field and the momentum. And from here, I can start doing quantization because I have some prescription of how to relate the operators to one another. Okay. So this is it. And what I showed you today was an example which is very simple, where the Lagrangian is just a function of only derivatives. It's also a quadratic function, and that's also why we get such a simple wave equation. Okay? In fact, we got a linear wave equation, a linear differential equation. It's not necessarily what you get. If I had in my Lagrangian terms that go like phi to the 4, I'm going to get a nonlinear equation. Okay? But I can get an equation of motion. Another thing that is a bit simpler for our case is that we have only one space dimension. So, but it's very easy to guess how to generalize it to higher dimension. So let's write the more general theory. So I can have D is the space dimension. Okay. And I can also have, instead of just one field, in my case, not only the space was one-dimensional, but also the displacement, I assume, it's along the chain, right? It's like a longitudinal wave. So the field phi is a scalar. It has only one component, right? And it can take positive or negative values, but only along one axis. But I can imagine, even in the one-dimensional case of the vibrations in a string, I can imagine longitudinal vibrations and transverse, right? And in fact, I can have the transverse directions in y and z, right? So my vibrational field, my phi, is actually not one phi. It has coordinates. More generally, I can have a field theory for a field, let me write it like this, which is some vector. And it can have components. Let's call them phi I. Okay, so phi 1, phi 2, phi 3. It can be many more. It can be. You can also think of a field that describes something like a spin. That's another example where it can have components, and it can be more than 3. Okay, it's not necessarily related even to the space dimension. Okay, it can be a complex number. A complex number, how many components does it have? 2, right? Real and imaginary part. So, more generally, if I have these space dimensions and a field with some components, I can write a Lagrangian density that will be a functional of all the components. Okay, so I goes from 1 to, I don't know, let's call it curly n. It's the number of components. And it can depend on the time, so it will depend on the time derivative of all the i's. And it can also depend on all the space derivatives. So how shall we write it more generally? We can write it like this, where mu is x, y, z up to d, and time. Okay? Okay, so you can have derivatives with respect to all the fields. All the dimensions. And, yeah?
What is eigen's n?
What?
It's big n from I1.
Yeah, n is the number of components. So,
Okay.
and curly n components.
Curly.
Yeah, so usually we want the number of components, unlike the number of degrees of freedom, which we already accepted goes to infinity. Usually we want this to be finite, and usually of order 1, right? I mean, but it can have a structure. It can be, actually it can also be, doesn't necessarily have to be a vector. It can be a tensor, something that has 2 indices, but also a tensor of finite size is characterized by only a finite number of components. Okay? So this will be the more general thing, and then the action will be, how shall we write the action? So it will once again be integral over time, but it will also be integral over space. And the space now has the dimensions. Okay? And then it's this phi I and d mu phi I, and this is a function that can have many terms because there are different components and their derivatives. Yeah? Okay? Is there a question?
It's
yeah.
It's degree of D or it's
what?
DD.
DD.
Ah, degree?
No, D is for like D is 1, 2, 3. So it's like, okay, sometimes you write it as DDR, right?
Okay.
But in this course, very often in books, you'll find that space dimension is described by an X vector, not R vector. Okay, that's just a notation that is very common, so you have to get used to it. Actually, you can also define, notice that when I look at this, there's an integral over several components of space and time. And there's no, none of them is more important than the other. In fact, there are some theories like exactly the theory that we discussed with the time derivative square and space derivative square, that the space and time behave exactly the same, right? So one can formally think of space and time as components of space-time, right? So it is quite common to define a hyperdimension capital D, okay, and this is where capital D is just D plus 1. Okay, so that the time is treated as if it's another component. Okay, for this purpose at least, for writing the action. Now, then we can get a minimum. If we want equation of motion, what do we need to do? The same thing, we need to look for minimization of the action with respect to the phi I by looking for this condition. But notice, because phi has many components, it's not just one equation. In fact, these are many equations because this is for all I and for all x. Okay? So, yeah, so of course it's for all x, because when we write the delta S, the delta phi, it's a phi of x, and that has to be satisfied for any x and any t, any x and t. But also, if it has several components, we have for each component to write this equation. It will give us a set of equations. Okay? And sometimes you have to work out. You will see examples in the homework. Okay? So, for example, if you have two components, you can have a Lagrangian that couples the two components, and you get a set of coupled equations, and you have to solve them. Okay? But yeah.
מה שאני זוכר פשוט, כשאנחנו היינו עובדים עם משוואות אוילר לגרנג' היינו רושמים כאילו את כל היינו יכולים להגיד פונקציה פייל כלשהי, ואז היינו באותם משוואות מתייחסים לכל הנגזרות מכל אתה יודע,
נכון, בדיוק.
ולא יוצאים לכל קואורדינטה בנפרד, אבל כל אחד מהפונקציות פייל הוא משוואה נפרדת. אז למה אתה רוצה ליצור משוואות?
Now, okay, so actually this was exactly the next thing I wanted to say.
Okay.
So we already saw what equation of motion you got for a very special case, which is the 1D chain. In that case, notice that I didn't write Euler-Lagrange. I didn't say Euler-Lagrange, right? What I did was explicitly calculating the left-hand side of this, and we saw that it gave us an equation of motion that had derivatives, second derivative on both x and t. Okay? Now what is the general thing? Okay? So I'm not proving it because it's a very, very simple generalization of what you did in analytic mechanics. But the way it looks for arbitrary D and arbitrary number of components is, and let me write it, it's Euler-Lagrange equations. So this is how it looks. It's first the derivative of L with respect to phi I. And this is what I'm writing is for all I minus I'll explain in a minute. This is the general Euler-Lagrange equations, where mu here, mu is space or time derivative. Now there is something I want you to get used to. You see that here I didn't write a sum over mu, but it should be. Okay, so this is a relativistic, this is an Einsteinian notation. You better get used to it. Is it? Maybe. For the derivative?
כן, יש לי הנוטציה זה שצריכה שאחד יהיה למעלה ואחד יהיה למטה, ואז כאילו זה...
Okay. Okay. I'm not actually sure, but yeah, let me... But I'm not sure it's true for a derivative though. Okay. Never mind. Okay, but what I mean here is actually very simple. What it means explicitly is derivative with respect to time of the delta L to delta of time derivative plus the same with x. So the sum of all these, actually this minus this should give you 0, yeah? What?
Efrat, I think you're supposed to have upper index
Maybe it's on the second
parameter
one.
and not on the outside derivative.
What? Sorry, say it again.
I think the upper index supposed to be on the delta and not outside on the.
No, the delta is
Yeah. You
there's
can
no
think,
index on the delta.
You can look at the Lagrangian like a function of the upper derivative, not the lower derivative.
You mean you want to exchange these two?
Yes.
Oh, okay. Yeah, fine. No, the truth is
It depends on the metric of the system.
Yeah. I'm not sure, it looks weird to me, but okay, let's leave it like this, as long as you know what I mean, okay?
Okay.
All right? So,
Now it's good.
actually, Sar is going to talk about this more systematically in the tutorial next week. He's going to go through metric and relativistic notations, but let's just so this is a set of equations which have to be satisfied for each component I, and so if I have curly n components, there are curly n equations, and in each equation here you have a summation over all the derivatives, but you also have a term which is a derivative with respect to the field itself. Okay? Now let's just check that in the special case of the 1D vibrations, the first term didn't exist. Let me just write it down quickly. So it was half m phi dot square minus half rho s of this, right? So what were the Euler-Lagrange equations? Let's check that this expression holds. The first term, what happens to it? No, look at L. Is there any depend? It's 0, right? Because there is no term that depends on phi itself, only on the derivative.
Ah, okay.
Okay, so the first term will be 0. Now, the second term will have two contributions. One is from the derivative with respect to, so I have to take the time derivative of the derivative with respect to phi dot. The derivative with respect to phi dot, let's do it quickly, okay? So I have the d dt of delta L delta phi dot, but what is this? It's just m phi dot, and if I take the time derivative the second time, I get second derivative, right? So this gives me a second derivative in time, and the last term is exactly the same, but with x. So it gives me a second derivative in x, and there's a relative minus sign between them, and therefore what I get is exactly the wave equation that we discussed before. Okay? So you see, this is just a special case, but more generally, we can also have things coming from here. And they may even give us something nonlinear. Okay? We'll see examples in the next lectures. Okay? But what I wrote here is just the most general Euler-Lagrange. So this is one of the equations that you have to know, and I mean, not by heart, but you have to use a lot. Okay. What else can we say generally? Basically, these things I can now generalize to many components and many dimensions. So we can define, and this is again for all I. We can define a momentum, and let me call the momentum pi I, which is a function of x and t, and notice x is a d-dimensional vector, this momentum is the derivative of L with respect to the time derivative of component I of the field. Okay? So each of the components will have its own momentum. And now we can also define a Hamiltonian density, which is, and again now we'll have to have a summation over I, which I also write implicitly as Einsteinian okay? So this is actually a sum over I. Okay, it's like a scalar product, if you like, of pi and phi dot, which are related by the first equation, minus L. And once we define a Hamiltonian density, we can define a Hamiltonian to be d dx of h. Okay, where h now is going to be a functional of all the components I, all the components I of phi, and, sorry, and all the derivatives, okay, and so on. Okay? So this is the most general prescription for doing field theory. First, find the Lagrangian. And once you have a Lagrangian, there are two directions you can take. One is to calculate an action, and from the action get equations of motion. Another direction is to go to Hamiltonian formalism by defining a generalized momentum operators, or not operators, sorry, fields, momentum fields, okay? And once you do it, you already have a good starting point for doing quantization. And we are going to see that all these, both these general prescriptions, first calculating action and defining Hamiltonian and defining generalized momenta fields, we're going to use them throughout the entire course, okay? For different problems. Yeah, I wanted to ask something.
It's little d and not big D over the ddx because the Hamiltonian doesn't have the time derivative.
Right, exactly. It doesn't have time derivative in it. It has exactly. That's right. I mean, the dynamics is embedded in the fact that you have a momentum dependence. That's right.
The new derivatives of VI also should be effective because it's send it with mu, but you said it
yeah, that's a good point. Yeah. So okay, let's not call it. Okay, so good point. Okay, so mu here is actually just the space indices. Yeah, that's right. Good point. Yes. Right, exactly. So the dynamics of a problem in Hamiltonian formalism is embedded in the momentum. Okay, once you have, because the Hamiltonian has momentum and coordinate dependence, or momentum and field, it has dynamics, and that's why you know, when you do quantization, the non-commutativity is embedded in the fact that you have two terms that cannot be simultaneously diagonalized in Hamiltonian, right? So, and that is what carries the dynamics, okay?
כן, הפאי הזה זה מה שדוחף את כל הדינמיקה מבחינת זמן והכל. אבל לצורך העניין, למה אנחנו יודעים שאין לנו נגיד עוד קורדינטות של זמן, או לצורך העניין, עוד כאילו של זמן לצורך העניין, יש לנו כל הזמן כאלה מחביות.
Because there aren't any, right? I mean, the description, we live in a space-time, and time is only one, okay? I mean, you can, I'm sure that people have written theories that have generalized things, but there's no physical motivation for it. From all we know, I don't see any use of it. Okay? Unless you want to, I don't know, at least in the physics world that we live in. So time is special, it's not just, but from a formal point of view, you may have a situation where time and space behave like they are components of the same thing, and these are actually relativistic theories, okay, where space and time appear in a similar, in a mathematically similar form. Yeah, you want a question?
Well, when you write D and degree or D, D you mean X, Y, Z? Like,
Yeah.
right here?
Yeah, the little d is the space. Okay, that's just a notation.
Why you write 3 points? Because you have more than X, Y,
No,
Z.
I mean in general you have.
What?
It can be actually if you. What I mean is just
X2.
x1, x2. Yeah.
Okay.
Up to xd.
Okay.
Yeah, that's more correct. Yeah.
ולמה את האינטגרל, אנחנו לא עושים איזה אינטגרל על משהו על תנא וכל זה, הרי לצורך העניין למשל הפעולה היה אינטגרל גם על הזמן. למה פה נגיד לצורך העניין איזה אינטגרל זמני?
There's nothing like that, okay? Just like, this is just like in the usual analytic mechanics or in any quantum problem. You either have a Lagrangian, in which case there is a point to define an action, and there is a Hamiltonian. And here it's just generalizing the same notions to the case that instead of just having 1 degree of freedom, we have infinity. Okay? That's all. That's basically it. So everything here is just a trivial generalization in a sense of what you know from dynamics of a single particle, but it's not so trivial because it carries within it information about the fact that the number of degrees of freedom is infinite, and inside the Lagrangian you can have or the Hamiltonian, both of them, you have derivatives. Okay, derivatives. If you want to convert it to the language of particles, like what we had in the beginning, they come from interactions of different particles. Okay, so they are not single body things.
רגע, אבל כשאנחנו עושים נגיד הכללה לצורך העניין, יש לנו הגדרה כוללת לפעולה. אז אמרנו שיש לנו נגיד צפיפות לגרנג'יאן ועושה אינטגרל כל דרגות החופש. למה פה אנחנו לא רואים הקבלה דומה בקטע של המילטוניאן? שכאילו אנחנו מתייחסים לזמן ולמרחב עוד פעם כאותו סוג דרגות.
Because again, so it translates to English, so the time and space are they are not the same. So when you talk about dynamics and equations of motion, they are not serving the same role. Okay? 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 And again, if you do have a theory where space and time just formally appear to have the same functional form, these are very special. And that's special, that's relativity. But it's very special. Okay? There is no reason that they will be treated in the same way. Okay? All right, so now what I want to do in the last half hour is to indeed show you an example of a different approach to deriving a field theoretical description that is not starting from a rigid and well-accepted microscopic description, because we don't have it, but rather starting from a wild guess, okay, in a sense. So, and the second example I'm giving you is electromagnetism, okay? So it's again a simple theory that you are familiar with. But what I'm going to start showing you today is that as well can be related to some field theory, and in fact it's very natural to relate it to a field theory, because electromagnetism from the start is formulated in terms of fields, not in terms of particles, right? There are no particles. The electric field is not made of particles. In fact, it does. Okay, there are photons, but we have to show why. Okay, but just classical electromagnetism is at least the 19th century electromagnetism is formulated in terms of what? What are the equations of electromagnetism? Maxwell equations, okay? Let's just write them down.
אז עכשיו אנחנו עוסקים בדוגמה שאנחנו לא נדע בדיוק את ההמילטוניאן.
Exactly, yeah. Electromagnetism. So in fact, in some sense, this second example, unlike the previous one, we started from writing the Hamiltonian, right? We knew how to write the Hamiltonian because we started from particles and the springs. And then we showed that we can get a Lagrangian and we can get the Euler-Lagrange equations. And the Euler-Lagrange equations gave us a wave equation. Okay? Now we are going to do the opposite. We start from the equations.
And we want to
The
find
equation, what we call the equations of motions, we know them. These are Maxwell's equations. We are going to go from the equations to a field theory that gives them. Okay? So it's the opposite way. So let's write the Maxwell's equation. So first of all, there is div B equals 0. There is, maybe they're not in the right order, but never mind. Div E is what? I'm using CGS units.
You assume you are in vacuum?
No,
Okay.
not in vacuum in general. Okay. Now let me write a curl of E.
אנחנו לא מניחים שהרוחה אפסילון 0 שווה 1 ביחידות אטומיות.
It doesn't matter. Let's, so I'm using CGS units where E and B have the same units. Okay. And epsilon naught or no, this is replaced by factors of 4 pi. And we have this. Okay, actually, let me write them. Never mind. Like this. This is right. Curl E is the time derivative of B, and we also have that curl B is time derivative of E plus, if this is in vacuum, but if you have current, there's also a current, right? Okay. These are Maxwell equations. They are kind of equations of motion that resemble the wave equation we got. In fact, we can plug them one in another and get a wave equation, right? For the electromagnetic radiation. But unlike the previous example, here I have how many components I have of the field. I have 6, right? I have 3, if this is in 3-dimensional electromagnetism, I have 3 a 3-vector E and a 3-vector B. Okay? And I have the derivatives are also in 3-dimensional space and time. Okay? Okay. Now, another thing you know from electromagnetism is that it is useful to define the E and B field as derivatives of some potential, right? You remember that? So there is first the electrostatic potential, which minus gradient is the electric field. But there's also a vector potential. And if you take the curl of A, you get B, and so on, right? So let me write it down. So E is minus grad of phi. Let me denote it by capital Phi plus time derivative of A, if A is the vector potential, and B is curl of A, right? Okay. And now I want somehow to define an object, a mathematical object, that formulates all these relations in one definition, and that is something I think you didn't see in your earlier studies. The electromagnetic tensor F mu nu. Did you see it in any course before?
Yes.
Okay, so some of you may have seen it. It's not really important. Let me just write a definition. Okay, I can define F mu nu. This is and mu here are space and time coordinates in 3 plus 1 space-time dimensions. Okay. So yeah, actually you usually write them as T and minus R, minus X, minus Y, minus Z. Okay, it's a 4-component thing. And and sorry, let me first. Okay, so I want to write here a definition. So it's T and minus X, minus Y, and minus Z. And you can also define a 4-vector, I don't know how you denote it, maybe like this, a 4-vector of A, the vector potential, which has a 0 component or a time-like component phi, and minus the 3-dimensional A vector. Okay, you've seen it? Okay. under this definition, I can define a two-component tensor, which is completely anti-symmetric. So it's d mu a mu minus d mu a mu. Yes?
Why it's minus have minus?
Well,
Minus
this
minus, why not?
because in relativity the metric is the space and time have different. Right, or the interval has time-like direction and space-like in the opposite side. Okay, this is convention from relativity. But this thing, if you try to plug in special cases for the a mu's and the derivatives, you see that it contains all the options. Now, because it's by definition completely anti-symmetric, right? So what will be the diagonal if I... So here mu and mu can be anything, but if I take mu equals mu, what do I get?
0.
I get 0, right? It's just, it's completely anti-symmetric. And because there are 4 components, so what is the size if I write it as a matrix?
4.
It's 4 by 4, right? It's 4 by 4. The diagonal is 0, right? So how many components are left to fill the tensor? Let's write it down. Here I'm writing the matrix F. Exactly, right? So because it has you need 6 components to define it. Right? What are going to be and it's also, you know that it's completely anti-symmetric, so therefore, how many components are left here? 12, right? It's 6 and 6, but these 6 and these 6 are related by a minus sign because it's anti-symmetric, right? So what are what is the number of independent components?
6.
Only 6. And these are nothing but the E and B fields. Okay? So in fact, if I write it explicitly, and you'll discuss it more in detail in the tutorial next week, the first row is the electric field. And let me just keep track of the signs. So this is minus BZ, BY, and minus BX. Okay? Yeah? Question? Okay, and this here, okay, you can fill it up by yourself. It's all completely anti-symmetric, okay? Okay, great. So, okay, why did I bother to define it? Now, I remind you what we are after. So, of course, we already know electromagnetism. There's nothing we need to solve here. But what I want is, I want to be able to write down a Lagrangian that from which the Euler-Lagrange equations will give you the Maxwell equation. Okay. Now, if I find such Lagrangian, I can do with it everything I can do with Lagrangian. In particular, I can use it to define momentum for generalized momentum. Although there's nothing mechanical here. And I can write a Hamiltonian. And if I write a Hamiltonian, usually there's some prescription by which I can quantize. And then I have a hope of getting a quantum theory for electromagnetism. Okay? That quantum theory will indeed give us the photons, but at the moment we don't have a prescription of how to write the Lagrangian from scratch, from a microscopic, right? Because there are no particles that vibrate. Okay, this is something that exists in a vacuum. Okay, but I do know what are the equations of motion. And another thing that I know is that there are some symmetry properties that have to be obeyed for the theory. Okay, what are the symmetry properties? First of all, there is Lorentz invariance. You know that one of the properties of Maxwell's equations is that they are indeed Lorentz invariant. You can go to a different frame, do a Lorentz transformation, they go back to themselves. So there is Lorentz invariance. There is another symmetry property that is included in electromagnetism. You remember that when we derive fields from the potential, either the vector potential or the electrostatic potential, there is a gauge freedom. Remember that?
Okay. Yeah.
So all the Maxwell equations are symmetric under gauge. What is the gauge? So for any component of A mu, you can make a gauge transformation to A mu plus a gradient of some scalar function. Okay, and again, this can be time or space component. Gamma is some scalar function. Okay, any such transformation is a gauge transformation that doesn't change the Maxwell equation. Okay, so if we think of the A, the four component A, as the basic field of our theory, then actually it is well defined only up to a gauge transformation. So this has to be a symmetry of the theory. And let me see, is there something else that I forgot? No, these are the main things. Okay, so these are symmetry properties, and I know that I have to. So I have to write down an expression for the Lagrangian that respects these symmetries, and another thing that it has to respect is that a Lagrangian is a scalar, right? So I have here a functional of something that is composed of a tensor, and this tensor is made of vector-like components. And I need to write something that will sum up to a scalar, otherwise it cannot describe energy, right? Right, exactly. And now this is where I'm starting to play a wild game, okay? And what I'm writing now is a guess for the Lagrangian, okay? And what is the guess?
Contraction.
It's going to be the simplest thing I can write that respects all these symmetries, and it has a hope of giving me the Maxwell equation.
You want an invariant scalar.
That's right. An
So
invariant
you-
scalar, exactly.
You will want
Exactly.
a
Now,
contraction
but
of-
this case, this the scalar has to depend on two objects. One object is the f mu nu, okay, because the f mu nu includes everything. The second object is, notice that in the Maxwell equation, I don't only have the fields, I also have some information about the matter fields, right? The charge density and the current. Or to put it more generally, I can define a full current where the zero component is the charge density and the current density is the space-like. Okay, so it's again a 4 vector. So I need to write, to include in my Lagrangian, first of all, I need to have an expression that contains the fields through the f mu nu and the matter through the j. And I need to write it in a form that is an invariant scalar, exactly as you said. Okay? Okay, so what is the form? I'm claiming that the simplest form I can write. I need to write an expression for my action or for my Lagrangian density that is an invariant scalar made of two objects, a tensor f mu nu and a 4 vector j.
שני האובייקטים זה f mu nu ו-j.
ו-j, yeah, exactly. So let me write it explicitly. It has to be. Sorry. I want to write it directly through the. So it has to be some functional of f mu nu, and of course f mu nu is. Is a function of x and t and the j. Okay? Okay, and this is the action, which is the integral over the space-time of the Lagrangian density. So let me write it like this. Okay? 4 is 3 plus 1. So this is the capital D, and now I'm writing the Lagrangian, and I claim that it should have the following form. Let me just check something. Yeah, so now I'm being more careful with the indices, upper and lower, because it's an Einsteinian expression for summing over all components. But notice that it has to be the same mu nu here, right? So in order to get a scalar, this is how I get a scalar. I contract them. Plus some C2 F mu nu J. Okay, so here I'm actually writing only, I'm contracting only one. Actually, no, let me write, sorry. Let me write something more. Sorry, this doesn't give me a scalar, so that's not what I wanted. So in order to get a scalar that couples to a vector, I mean, I could have something that goes like J mu, but if I want the simplest one that is like the the simplest one in the sense that it appears only to the lowest power, then it couples like a scalar product of A, for vector A and J. Okay? So here actually the coupling to the matter field should better have the A itself and not the F mu. Okay? This will give me a scale. Right? You agree? Right. Exactly. Okay? So, of course, this is not the only option, right? In fact, how many terms I can add terms? How many terms I can add? Infinite. Because I can take this square, or this square, or, I can have any combination that contract all the indices to the 17th power or more will be allowed, okay, by symmetry and all the requirements. But, okay, so there are corrections, infinitely many of them. Miraculously, they are not there, at least if we are in a vacuum. Okay? In fact, if I want to describe electromagnetism inside the material, and especially nonlinear optics, when you can have a dielectric response that depends on the intensity of light, for example, these kind of things are described by corrections. But electromagnetism in vacuum, not in vacuum, but not in a linear, let's say in a linear medium, electromagnetism in a linear medium is essentially stops after these two terms. So it's the simplest, as simple as you can guess. Okay? Yeah, so maybe I should slightly explain it. What I mean by a linear medium is when you have a dielectric constant that is just a constant. It can depend on okay, let me think if it can be non-homogeneous, but what I mean by a linear medium is that it doesn't depend on the intensity of the light. Okay, it just depends on the material. It can have space dependence or frequency dependence and so on, but not on the intensity. A non-linear medium is when you actually have strong light changes the medium, and that's more complicated. Okay. But if we forget about this, then this will give us, in fact, the correct theory. And notice that here there are two coefficients of which I know nothing about. Okay, I mean, they are just constants. Now, and why at this point I cannot say more than this, because it's a guess. This is a guess, okay? And the guess is based on accounting for all the symmetries and writing down the simplest theory that observes them. Okay? That's the guideline. And that's what you do in field theory in more complicated cases where you don't know the answer. And you just try. You write the simplest thing and try to see if it gives you the physics. Okay? And the guideline is that anything that is allowed by the symmetry can be there. Okay? Now what you're going to show in Actually, in the tutorial, I'm not going to go on with this in the lecture, but in the tutorial next week, what Sar is going to show you is, first of all, you're going to find what are the coefficients, such that you will get the Maxwell's equation, and you will get them, and they are indeed the Euler-Lagrange equations of this theory, just the way we defined it in the generalized theory, except that now our phi i's are the 6 components of F mu nu, okay, and the components, and this describes, of course, from here you can easily see that when you take derivative with respect to A, you will get linear coupling to the matter field, something like rho and J, right? And so it will come from Euler-Lagrange. Second thing, very nice, that you're going to show is that you can also define momentum fields. Okay? So if you think of E and B, all components of them as some fields, each field has a momentum in the exact sense that we define it in the mechanics example. And if you define the momenta, you can define a Hamiltonian. And the Hamiltonian, what do you think, what would be your guess how it will look for electromagnetic field in a vacuum? What is the Hamiltonian
plus
really?
B squared?
Exactly, right? This is just the energy or the energy density of, so the Hamiltonian density is indeed going to be B squared plus B squared up to a constant. Okay? And all of this you'll see in the tutorial. And I guess that's a good place to stop. And what we're going to do next week in my lecture is to go back to the mechanical problem of the string and do the and start doing quantization. Okay? Okay. So thank you for your attention. Okay.